Why you no work?
He's failed at the first hurdle. That should totally, I tested that and everything. So Mark broke his laptop, and he doesn't get his new one until tomorrow.
Space broke my laptop.
Space? Outer space? Or?
Outer space. I was on a plane, and I was watching Spider-Man Far From Home on my laptop, like you do, and then it just went off. And now it won't work unless it's plugged in. And I've lost the plug. Oh, anyway, never mind. Let's talk about how JavaScript happened. And if into that title you want to read, and how can we stop it from happening again, you're not entirely wrong. Also, I tweeted, I'm going to go and talk to LD Nug about how JavaScript happened. And somebody replied, simple, good men did nothing. But yes, and so, but you know, we like to knock JavaScript. I found this while I was researching this talk. This is Flon's axiom. There does not now, nor will there ever exist a language, a programming language in which it is the least bit hard to write bad programs, which is entirely true. I have seen bad programs written in every language. So how did we get here? Well, there used to be no computers and no programming and no anything at all for a very, very long time, thousands of years. And it must have been nice. Everyone had a pastoral existence and worked outdoors with their hands and lived to about 30. But no, and then in the 19th century, this young lady came along. This is Ada Lovelace. Ada Lovelace was the daughter of the romantic poet and pan-European syphilis incubator, Lord Byron. And Ada's mum quickly decided that the best thing she could do for her young daughter was to keep her the hell away from her dad. And so she got a bunch of tutors, and Ada learned maths and lots of languages and engineering and all sorts of fabulous stuff. And her mum sent her to salons. And salons were like clever people getting together and going, oh, this is how I've been clever. Quite a lot like user groups, actually. And she went to one of these where Charles Babbage was presenting his engine, whichever one it was, Difference or Calculate. I think it was the Difference engine. And she got chatting to him and he explained how it worked. And then there was an Italian author who had written a book about this thing. And she went, can I translate your book into English? And he said, yes. And so she did, but she added a bunch of thoughts of her own. And one of the things she added was this program in the background here, which calculates Bernoulli numbers, whatever the hell Bernoulli numbers are. And so, yeah, she invented the notation for writing the program down herself, and then she wrote the program. And so that's the first programming language, that's the first program, that's the first computer programmer. And then nothing at all happened for about 90 years, because Ada, sadly, she died very young. She was 37, I think, when she died. It was very sad. And yeah, and then Babbage went through this whole thing, of course, because he was going, oh, I've invented computers. And he went to the government and said, give me £500,000 to build a computer. And they went, okay. And because he was posh and rich, so if you're posh and rich, the government will give you money. It was always been the way. And then he got halfway through building it, and then he had a better idea. And who's been there? Yeah. And so he went back to the government, give me £1 million. And they said, no. And so it all kind of stalled until 1940. And then we decided, as a continent, that it would be a brilliant idea to have another war, because the last one had been so good. And actually, the rest of the world had watched this and went, yes, no, it was fantastic. We're going to join in this time. And so the Americans and the Japanese and everybody got involved. And
not a historian.
I am not a historian. At some point when I'm not being broadcast live on YouTube, ask me who the one person responsible for both world wars is. And if I don't think you're going to cancel me, I will tell you. But yes, and so there was a war, and there were like teams in the war, and they wanted to communicate with each other. They wanted to send messages, but you can't just send messages over the radio going, gather all the tanks, we're going to blow up this library or whatever. And so they wanted to encrypt their messages. And the Nazis used these. That is an Enigma machine. And the Enigma machine had billions and billions of possible combinations of which dials you were using and where you started them, and then patch cables in these holes in the front here. All these possible combinations. And it was thought to be uncrackable. Hello, do come in. We're talking about Enigma machines. And yeah, billions and billions and billions of possible combinations. And it was uncrackable, except that at Bletchley Park, just up the road, Alan Turing built one of these. Actually, I think he built two of them. And this is a bomb, and it's based on a Polish design. And I want to just give the Poles a lot of credit here, because they were the first people to capture an Enigma machine. And they did the initial work on the machine that was used to crack the Enigma code. But yes, and then this was used to work out the settings for the Enigma machine for a given day, and then you could decode all the messages for that day, and you could find out that the Germans were planning a surprise attack, and then you could let it go ahead anyway and let thousands of people die, because the alternative was to stop it, and then the Germans would figure out that you'd cracked Enigma. So yes. But then, not because they thought Enigma had been cracked and was insecure, but just because they could, the German High Command switched to using this. This is a Lorenz cipher machine, and for the ultra-secure messages, this is what they used. And where the Enigma machine had billions of possible combinations, this had like quintillions. It's more than the number of atoms in the observable universe, or something like that. And so it needed a better machine. This was the better machine. This was the Colossus. We built this. This is a sort of programmable computer. It's not programmable, but it's configurable. You run a bunch of patch cables, and then that sets the program, and then you turn it on, it does the thing, and it spits out the decoded message. And then the war ended, and we smashed it into tiny little pieces, and all the design plans for it and schematics and blueprints and everything else were covered by the Official Secrets Act, and we only found out that the damn thing ever existed in the 1990s. Which means that for a very long time, this was the first computer. Actually, this one, but for a long time, it was this one, ENIAC, the Electronic Numerical Integrator and Computer. And that word just at the end there, computer. So at the time that this was built, computer was a job title. You could go and apply for a job to be a computer and essentially do sums. NASA employed a lot of computers in the 1960s. If you watch Hidden Figures, one of the women in that, her job title was computer. But the ENIAC, it was like Colossus. It wasn't programmable in the way that we would think of it. It was run cables between different holes. And they got a bunch of women to do this who had an aptitude for maths and had worked on switchboards during the war, because they were very good at swapping cables around and stuff. And so these were the ENIAC programmers, 6 ladies, and the ENIAC designers and builders never bothered to document how the thing worked, and so these women had to figure it out for themselves and then make it do useful things. So that's in sort of like the late 40s, early 50s ENIAC. And then IBM, who had been building sort of adding machines and calculating machines and this sort of thing, released the IBM 701, which was a gigantic, great big thing. And the first mainframe computer. Massive, massive thing. And this was used for doing sums. They weren't doing anything complicated with it. We didn't have like databases and that sort of stuff at the time. It was just put in some numbers at this side, get some other numbers out at that side, job done. And they used it for things like calculating trajectories for missiles and shells and that sort of stuff. If I put this much gunpowder in a cannon and fire it at that angle, where will the cannonball land? And the maths is not that complicated if you know what theta means, which I don't. I recognise everything else there, but I don't know what theta is supposed to mean. Oh, hang on, it's there. It's the angle. There we go. Anyway.
Theta is maths for angle.
Theta is maths for angle. There you go. Exciting stuff. But the problem was that you could know this formula and you could be able to apply this formula. But if you wanted to teach a computer to apply this formula, you had to take this very sort of simple sum here, and you had to turn it into machine code. You had to know the opcodes to do all the things you could do to numbers in the memory of an IBM 701, and then you had to put them all together in the right order. It was basically assembly programming, except without the mnemonics. The words. So you didn't have LDA and JLE and those sorts of things. You actually just had to know the opcodes itself. Right. Then this guy comes along. This is John Backus. John Backus had got his degree and was wandering around in Manhattan, and he walked past IBM's offices, and through the big windows he could see the IBM 704 prototype, the sequel to the 701. Not sure what happened to the 2 and the 3, but never mind. And he looked at, he saw all the flashing lights, which incidentally didn't do anything. They were mainly a marketing exercise. And he went, oh, that looks brilliant. And he went inside and said, hello, can I get a job doing something with that, with the lights on it? Because it looks fun. And they went, yes. I think they did an aptitude test or something, but they went, yes. And so he goes, yay, I'm a computer programmer, even though I don't know what that is. And so then he sat down and he saw the opcodes and he went, oh no, that actually looks quite dull and boring and difficult. I don't want to do that. Because John Backus was a lazy man. And we should be thankful that John Backus was a lazy man, because lazy people, the world needs lazy people. Hire me. The world needs lazy people. Bill Gates says, I choose a lazy person to do a hard job because a lazy person will find an easy way to do it. And John Backus looked at programming and went, there's got to be an easier way. This computer transforms input into output. So what if the input was like more like English, and then you put that in, and then the output is the machine code, and then you take all those cards out of the hopper and you go back to the input side, and then you run them in again, and then that loads the machine code, and then you load the data. And so, yeah. And so he went to IBM and said, well, this idea for this thing, can I have a brand new guy, fresh through the doors, can I have a team to build this? And IBM said yes. And they gave him a bunch of people and they all went off and essentially hid for like 2 or 3 years. And IBM moved them around the place to different offices and rented offices. And sometimes they had to stay in hotels in the city so that they could be close to the office because they were working in shifts and all that sort of stuff. And between them, they came up with a software application that would take formulas and translate them into machine code, a formula translator, Fortran. Fortran came out in 1957, and it looked like this. So we have a program declaration at the top here, FizzBuzz. We're going to see FizzBuzz multiple times. And then we say do, down to line 40, set I to 1, and then count up to 20. If the modulus of I and 15 doesn't equal 0, go to 20, otherwise print FizzBuzz. There were no string constants. 8h said anything on the rest of this line is a string, and then continue, which jumps back up to the do. Otherwise, it's gone down to here. And we say mod 5, then print buzz and continue and go back up to there. But if it's not, then we go to 30 and then we do the mod 3. And then down here at line 40, we say asterisk comma, print asterisk comma I, which just prints the value of I. And then this end doesn't actually loop back up to here. So this end is the end of the program. And so it loops back up to here because of the do 40. And so this is kind of the a for loop, but they didn't call it a for loop. Yeah, so jump back. Right, so I equals 1. And we still use this today. If you create a for loop to go through an array, you will use I. If I'm working with you and I come along to review your code and I see that you have not used I may very well put one of those nit comments on your code and go, why are you using A as the index variable? Because it's just wrong. No, we use I. And there's a reason why Fortran used I, and that is essentially the same reason why every other language we've used I along the way, because Fortran got there first. Fortran had 2 data types, integer and real. And in the first version, the 1957 version of Fortran, if you wanted a variable to be an integer, its name had to start with I, J, K, L, M, or N. All other variable names were real. And so if you need an integer, you go, what does it have to start with? I. Well, I'll just call it I then. And so yes, and we still today use this. The reason why Fortran used I, J, K, L, M, and N is that they tend to be used as the indexing character in sort of continuous mathematical expressions. But yes, like Zi and Zi plus 1 and Zi plus 2. Don't know why Z. Actually, I do. Jonathan Coulton.
So if you ever need to remember how to spell Edgar Dijkstra's name, IJK.
Yes, IJK.
Yeah. And you can tell junior devs we use IJK in honor of Edgar Dijkstra.
Yes, but it's not true.
And if you don't know who Edgar Dijkstra is, that will make no sense at all.
He's coming up.
He's coming up.
So yes. So yeah, that's why we use I as our index variable. Now this is the Fortran code, Fortran 57, it's factorial. N is n times this, times that, times that, times that, times that, and then print n, and then end. And right up until it was just about to release, because they'd essentially been just writing things on punch cards, they were using the multiplication symbol, not the character X, the multiplication symbol, to represent multiplication. And then when it came time to actually release this thing, somebody looked at the machine that you use to type punch cards and went, this hasn't got a multiplication symbol on it. And they went, well, what has it got? What's the closest thing? Probably the asterisk, I suppose. And so it was switched to be the asterisk. And again, this is why we use the asterisk for multiplication, because Fortran punch card creating machines didn't have a multiplication symbol on them. That's a Fortran punch card. And each column here is a character. So we go from 0 up to 9 for some reason, but actually only the first from 1 to 7, I think, we use for characters. And then there's other bits and pieces on there. But it's 80 columns wide up to here. And when teletype terminals came along, they were made 80 columns wide because punch cards were 80 columns wide. And so if you wanted to display a punch card on screen, you would need it to be 80 columns wide. That makes sense because teletypes and things sort of in the same era and it had to be set somewhere. But out of the box, Visual Studio Code, NeoVim, Visual Studio, JetBrains Rider, whatever editor it is, they still have the word wrap set to 80 columns. And we're still, us with our ultra-wide LG OLED 39-inch monitors. And they're going, no, 80 characters because Fortran. So this is what we get from Fortran. We get the if statement, we get asterisk for multiplication operator, we get I as the iterator variable, and we get the default setting of 80 columns for word wrap on any IDE. And they shipped Fortran, unusually for IBM, actually shipping software. Don't know whether it was on time and on budget. But they shipped Fortran, and almost immediately, programmers did what programmers do, and they started hating on it. None more than this guy. This is Edgar Dijkstra. And he is most famous for saying "go-to considered harmful." This was an essay he wrote, and what he was essentially complaining about was all these go-tos all over the place as the only way of controlling program flow just makes a mess, and what we want is more structured code. He said a lot of things. Go and look on like QuoteBrain or whatever for Edgar Dijkstra quotes, but this is my favorite. If debugging is the process of removing bugs, then programming must be the process of putting them in. And so he advocated for structured programming, being able to break your program down into meaningful chunks and represent your thought process more sort of clearly in the code. And the result of that was Algol. And Algol was designed, the first programming language to be designed by a committee. And you can sort of tell one key thing that lets you know that Algol was designed by committee is that in Algol 1958, it is impossible to write FizzBuzz, or indeed Hello World, or anything that prints output, because Algol 58 had no way of writing output at all. If you wanted to run an Algol program, you basically checked the contents of the registers, and then you ran the program, and then you checked the contents of the memory again by kind of using the bits on the machine. So this is a slightly later version of Algol. I think it's Algol 60. This is FizzBuzz in Algol 60, and we have a begin and an end, because of course we do. That's kind of like the program class and the main method. And Microsoft kind of went, oh, we don't need that, we can have top level. But yes, and then we declare the type of I to be an integer. Fortran actually added declared types a few years later, where you could then say, this is an integer and this is a real, which led to the brilliant Fortran joke, God is real unless declared integer. Just Fortran joke then, not brilliant. But yes, and so then we get a for loop for I colon equals 1 step 1 until 100, do, begin, end. If something, then outstring FizzBuzz, else if, else, and so yeah, Fortran didn't have else, it didn't have else if, it didn't have any of that stuff. It was either if something, do something, go to something, or if something, go to something, otherwise carry on. But there was no else built into it. And so yes, and we have hard-coded strings in double quotes, and those are treated as strings by the compiler. And we have semicolons at the end of statement lines. And so Algol introduced a whole bunch more of the things that we use in modern programming. And it also, so there was this committee and they met and they defined Algol, and John Backus was on that committee, because if you were inventing a programming language in 1957 and you wanted somebody with experience, there were only like 8 people in the world, and they were all in New York. And so John Backus was on this committee, and Dijkstra was on the committee, but he consulted with them. But John Backus went, if we're going to define the way this language should work, they had no intention of implementing it. Okay, they were designing it for other people to implement. And so they needed a way to describe it. And so John Backus invented what was called Backus normal form, which was a grammar for defining programming languages, defining the tokens and everything else. And then a guy who was also on the committee called something Naur, N-A-U-R, suggested some improvements and modifications to Backus normal form, and then somebody went, oh, you should call it Backus Naur form, and so they did. And to this day, BNF is the standard way if you invent a programming language. Do you have a BNF for Rockstar? Yeah. See? Stupid fucking programming language. But there's a BNF grammar for it. And so Algol, we get the block structure, we get if, then, else. Algol also had the switch statement, or case, if your language gets those the wrong way round. For loops that were actually called for loops rather than do loops. It had functions, it had the semicolons at the end of lines, which JavaScript adopted and then made optional. It was the Algol committee, or it was people on the Algol committee that came up with the Backus Naur form that we still have not found a better way. And the nice thing about Algol, so Algol was completely unsuccessful in terms of people using it to build stuff, but it was super useful in terms of research into programming language design. And there were hundreds of spin-offs of Algol. So there's like versions of Algol. There was a 58, a 60, a 63, a 68, and so on. But there were also kind of spin-offs of Algol, like the Better Call Sauls of Algol. And there's one of them in particular that contributed something to the totality of programming language design and software engineering that I think deserves a special mention at this point, and that is Algol W. And Algol W was the first programming language with the concept of records, or structs, sort of collections of information that were all tied together, like a first name and a middle name and a last name and an address and all these sorts of things. And these were records. And so if you had a person and there was a field for a spouse, let's say, and this person was not married or recently separated because his wife decided she could do better, maybe heart less on sleeve, then you needed there to be a way of saying there is no record at this location. And so Algol W invented null, because of course it did. And so yes, you would have your record here, which has got integers f1, f2, and f3, and then we have a reference to that record, which is a reference type variable, and then we assign null to it. And this was done by Tony Hoare, H-O-A-R-E, and he has since called it his billion-dollar mistake, and I think he's undervalued it. But yes, if you'd ever wondered. Of course, JavaScript took the concept of null and went, just one null? No, we need more than that. We shall have null. We shall have undefined, because you might have a variable that you've forgotten to set to null. So we'll call that undefined. And there's another one.
I always thought undefined was like the Donald Rumsfeld variable.
Yes.
Null means we know we don't know, but
yes.
If we don't know that we don't know, that's undefined.
Undefined, not a clue.
Yeah.
We might know, we've just forgotten to say. So yes. I was talking to you about this earlier on the podcast. So every programming language that exists owes something to Fortran, with the possible exception of this one, Lisp. Lisp just completely left field. Totally nothing to do with any of the others. And Lisp was created by this guy, John McCarthy, who was working at MIT and he was working in the AI lab with Marvin Minsky and a whole selection of other, unfortunately quite undesirable characters, it turns out, after some time. And they were working on trying to make computers think, which, given where we are here 70 years later, was incredibly optimistic.
They were, what, 5 years away?
They thought they were 5 years away. Yeah. Computers just needed to get a little bit faster. But they decided that the way we think is that our memory is just lists and lists and lists of things. And then when we get stimulus, that is a list of things. And then we compare that list to the other lists that we've got in our memory. And then that creates our reaction. And so they wanted a programming language that was very good at processing lisps, a list processing language. So they created Lisp. This is FizzBuzz in Lisp. Common Lisp. There are many Lisps, and then there are things which claim to be Lisps which aren't. But yes, and so Lisp, we say define a function FizzBuzz, and then we say loop for n from 1 below 101 do. And then let divisible by 3 and divisible by 5. So we're going to declare a couple of anonymous type functions here. And then we have a conditional, and then we say and divisible by 3, divisible by 5, write FizzBuzz. Otherwise, if divisible by 3, then write fizz. Otherwise, if divisible by 5, write buzz. Otherwise, format the input as a string. And then close all the parentheses. If you've ever worked at a place where they've got some Lisp code because it was written in 1970 and nobody's updated it yet, you can always spot the Lisp programmer because they're sitting there and they're typing and they're going 8, 8, 8, 9, 9, 9, 9, 9, 9, 8, 7, 6, 5, 4, 3, 2, 1, done!
Do you want a bad Lisp joke to go with your bad
Fortran
joke? So if you look at the listing there, you'll see that the divisible by 3 and divisible by 5 have 0p. And there's a convention in Lisp that anything which is a predicate, which returns true or false, ends with a p. So yes. 0p, if it's 0, it's true, and if it's not.
Yeah.
And Bill Gosper, who was one of the great Lisp hackers back in the 70s, was dining in a Chinese restaurant and wanted to ask another Lisp hacker if they wanted to share a bowl of soup. So he asked split pea soup. As you were.
Mm-hmm. Moving on, has anyone programmed in Lisp at all, or Scheme, or any variant thereof?
Has anyone programmed in JavaScript? Because if you programmed in JavaScript, you programmed in a Lisp dialect. You just don't know that.
You have, and we will come to that. Spoilers. So the point with Lisp is that everything in Lisp is a list, including the program itself. So this loop for n from 1 below 101 do, that's a list containing the atoms loop and for and n and from and 1 and below and 101 and do, and then another list. Okay? And the way you process lists, obviously, is you take the first item off the list and then you process the rest of the list. And Lisp, Scheme, doesn't matter what you're using, they have operators for taking the first item off a list and returning the rest of the list after that first item. Can anyone tell me what those two operators are? Car, C-A-R, and cdr, C-D-R. Not head and rest or anything like that. Car and cdr. And this is why. This is the register layout from the IBM 704 on which the first Lisp was implemented. And I don't know if you knew this. I didn't know this until I started researching history things. The idea of bytes didn't come along for a very long time. For a long time, we just went bits. And there was a point when a bit cost like $1 in terms of core memory. And so you could essentially say any number of bits. And IBM, for the 704, for their registers, went 36, that's a good number, let's have a 36-bit register. And then they would split that, and so you have your first 4 bits of the prefix, and then you have the decrement register, and then you have a tag in the middle, I'm not sure what that was for, and then you have an address register. And so the decrement register was used to contain the address of the rest of the list, because this is a linked list, so that's like next. And the address was used to hold the actual value of the first item in the list. And so CAR stands for contents of address register, and CUDA stands for content of decrement register. And that's got nothing to do with how JavaScript happened, but it was too good not to share, so Q. To me, that is the best example I've ever come across of an implementation detail leaking into the user experience. Because to this day, Lisp programmers are going, why, what, why is it CAR and CUDA? And which way round do they go? So yes. But Lisp introduced the idea of first-class functions, but it also introduced the idea of a heap, because lists, and we have pointers to the rest of the list and pointers to this and so forth. And so if you've got pointers to things, well, those need to be somewhere. And so they go on the heap. And so Lisp had a heap, and because it had a heap, it needed a garbage collector. And it had a garbage collector. And actually it had a primitive sort of JIT, but we'll come back to JITs later on. But yes, the main thing that JavaScript, I'm going to say took from Lisp, even though that's not quite right, took from Lisp is first-class functions. And then, Simula, 1962. If you say to most people, what was the first object-oriented programming language, they'll say Smalltalk, and they're wrong. The first object-oriented programming language was Simula, which was created by a couple of guys at the University of Oslo in Norway. And this was basically Algol with object-oriented features on top of it. And so here we have Simula. We declare a class printer, which has got a procedure print, and then we put our out text and everything in there. You can kind of see that it's Algol, but not. We've still got the semicolons at the end of the lines. And then we say ref printer p equals new printer. 3 will be fizz, 5 will be buzz. So this is like polymorphic and parameter driven and everything. And then we just run that through there. And so Simula introduced the idea of classes and inheritance and polymorphism, and also scope or visibility. So where you've got members of a class, like procedures and fields and whatever else, Simula had the ability to declare them as public, private, protected, possibly not protected and internal, because those are C# things, and that came sometime later. But yes, you could have private members and hidden members, which JavaScript completely ignored. So, and then I've got this coming kind of straight off Fortran, but let's talk about APL. APL was created in 1967 by Kenneth Iverson. And Kenneth Iverson wanted to make programming more instinctive, more just like you could have a thought in your head and very easily get your thought down onto the page. And so he invented his programming language, and it was called APL, which stands for a programming language. Yes, and I once met his children. They were called a son and a daughter. But yeah, he created APL purely as a teaching language to teach programming at the school where he worked, which was one of the big posh American schools. This is FizzBuzz in APL. That's the whole thing, one line of code. And actually half of it is declaring the FizzBuzz, fizz and buzz things. And then I knew when I wrote this talk what was going on here. I do this talk like every 3 months. It's gone. I have no idea. What I do know, though, is that you feed into it an array of the numbers from 0 to 100, and then you do a single operation against that array. In APL terms, you just go FizzBuzz that entire array, and it will go through and it will do everything to that array up to 100. And so it's very, very good for parallelizing code, for sort of being able to write code that the computer can then intelligently go, yeah, we can run this across all the cores, or we can use SIMD or SSE or whatever. But yes, if you're paying close attention, you'll be able to see that's not a W. That's not a W. That's not an L. That is an orphaned umlaut. It's an umlaut that has lost its O. And somewhere around there's a band called Motley Crue all of a sudden instead of Mötley Crüe, which is their actual name.
Surely one of those is a mod somewhere.
It's bound to be, but I honestly, I don't know how this works. Anyway, so yes, this was the keyboard that you had to buy if you wanted to learn APL. It is a keyboard with all the usual things on it, and then an extra shift key, and if you hold that down, you type these. And for a long time, I've just been going, ooh, that's completely mad, APL, what the fuck? But then I remembered I had a ZX81, and I had a Spectrum. And if you were writing basic code on either of those, you didn't type print, you pressed P, and it typed print for you, because to save memory, they'd given a single byte value to each of the commands that were on the keys, and so it would be stored as the print byte value, but then it would write print on the screen. And so actually this is quite similar to Sinclair machines from the 1980s. This was supposed to be Conway's Game of Life, which is also just one line in APL, but unfortunately there was an incident with a laptop and a job, and I had to recreate the slide deck from scratch, and I've messed it up. And so this is just FizzBuzz again. But Conway's Game of Life it's more squiggles, but it's essentially the same kind of thing. But the main thing that APL brought along was dynamic typing. So before that, every variable was either an integer or a real, or maybe a string or a character or something. APL, the only data type it's got is arrays, and into each element of an array, you can put whatever the hell you like. You can put a string in one element and an integer in another. And so APL brought along dynamic typing. Thank you, APL. Right, B and BCPL and CPL. And actually those should be the other way around. There was CPL, then there was BCPL, then there was B, which were all kind of based on each other. And these grew out of Algol in the 60s. This is FizzBuzz in BCPL, I believe. And so we got modules. So now we can share libraries and not have to write the same code over and over again. But yes, we have let's start be this, and then it's actually just declaring the start method, which I think is like the main method. And then we go through, we've got rid of the semicolons at the end of the line. So we could claim that JavaScript invented automatic semicolon insertion based on this, but I'm not going to claim that. But what we do have in here is curly braces, and BCPL was the first language that didn't have begin end or do end or words to delimit blocks. It used curly braces because much nicer and cleaner, and it makes code look a little bit exotic and just a tad sexy. Except, of course, that they were working with the EBCDIC character set. And what didn't the EBCDIC character set have? Curly braces. And so if you had curly braces, you could use them. But if you didn't have curly braces, you could use $paren and then $close paren instead of your curly braces. So BCPL gave us curly braces unless you didn't have them, in which case it gave you $paren, which was like Lisp but with money. But out of those grew C. And I think this is probably we can safely say where things really started to go very wrong indeed. My first job, I worked at a place where they let you teach yourself computing using their Unix boxes, and then went and hired you out for contract stuff. And you turned up on your first day and they just gave you this book, the C programming language, and said, work through that. And this was the first learn a programming language book which used Hello World as the first example. And so, yes, C gave us that, or Kernighan and Ritchie gave us that. Anyway, this is FizzBuzz in C. Include standard input-output, int main void. So we have a function that returns a known type, doesn't take any parameters, so we actually say void rather than just not putting them in there. And it kind of solidified the whole thing. It kind of went, yep, we're using curly braces, statements will end with semicolons, block things like for and if and so forth won't end with semicolons. We will use print f for this, we'll have for loops, but C was the first language that had this form of a for loop where you have an initializer and a condition and a modifier. What a lot of people don't know, if they've never done C programming or a programming language that imitates C to the correct degree, is that you can put as many initializers as you like in here, comma delimited. This works in C# as well. And the condition here can be whatever you want it to be as long as it evaluates to a Boolean. And the modifier can be anything you want as long as it changes whatever it is you're doing the condition against. You can put insane things in for loops. I was once helping a friend of mine who was learning C++ with her homework, and the homework was to validate that a string of characters was a valid ISBN number, book, whatever. And I sat with her and we wrote the kind of proper version of it. And then I went, give me a minute. And I refactored the entire thing into a single for loop that just had a semicolon after it. And I said, right, hand that in for your homework, and then hand that in and see if it gets you extra credit. And apparently what it got her was advice never to let me help her with her homework again. Because C let you do that. C let you do this, because this is also FizzBuzz written in C. Even though you can't actually, there's no fizz in there, there's no buzz, there's nothing, but that is FizzBuzz written in C. And it's so possible with a combination of the fact that it's kind of a spidery language anyway, and then you have its macro system which lets you hash define anything to be anything else. And yes, you can hash define true to be false and false to be true. And so you can write really, really hideous code in C. There is a competition, the International Obfuscated C competition that runs every year where people send in ridiculous things. Somebody once got a special mention but didn't actually win by submitting an empty file because there was a particular C compiler that would do something with that empty file.
So Simon Rysinkiewicz was the guy's name. It was 1996, and he submitted a 0-byte file and said if you compile it with this compiler, the compiler had a quirk that if you gave it empty input, it would produce a C program that produced no output. And so he argued that that program printed its own source code.
It was a quine.
And they gave him an award, and then they changed the rules to say that your obfuscated C program had to be at least 1 byte from then on. Otherwise, it was just a copy of his program, which kind of makes sense. So yeah.
And it's possible to write obfuscated code in any language, and it's a brilliant way of ensuring job security. But JavaScript, when people came to JavaScript and went, I wonder how you could write obfuscated code. Dylan has a whole 5-minute thing on this. This is FizzBuzz in JavaScript. It is. I promise you, that is FizzBuzz. If you were to take this slide deck, copy and paste that into the JavaScript console, it would print, or console.log. And I'm really not sure how it got as far as console.log, because it doesn't say console.log in there anywhere. But yes, you can essentially add and subtract and index, and that's all you have to do in JavaScript, and you can produce, and you will find things where you can write normal JavaScript code and then it will produce this, which is just horrible. So C gave us the C style, what we now call the C style of programming language, and it gave us hello world as your first program example, and it gave us truthiness. So before this, all programming languages had a concept of a Boolean expression, but it had to be this equals that, this modulus, this is 0, 0p, whatever it might be. C was the first one that went, any non-zero integer is true, including minus integers. So 0 is false, any non-zero one is true, which is why in C you can write while C equals getchar, and it will terminate when it reaches the end of the file or the end of the line. And we also get obfuscating code for fun and profit. Mainly fun, though. Same year as C, Smalltalk came out and really should have taken the world by storm. If you compare Smalltalk to C, C was a sort of minor evolution of B, which was a minor evolution of CPL, which was a minor evolution of Algol. Smalltalk was revolutionary. Smalltalk was created at Xerox PARC, the Palo Alto Research Center, and it was mainly created as the programming language to build applications for the world's first GUI desktop operating system, which never actually got released, and made it out into the world because somebody made the very, very silly mistake of saying, hey, Steve Jobs, do you want to come and see what we're working on? And they gave away the farm. But actually you could see there was quite a lot of Smalltalk influence in Objective-C, which was the programming language for Macs. But the difference, so when you're creating character-based applications that used to run in DOS or Unix or whatever, you would print something on the screen and then you would say to the user, you'd ask them a question. You'd say, or choose something from a menu, and they'd go, oh, I want 3. And it was very, very basic, horrible stuff. A graphical user interface, you've got a whole bunch of things just floating around on the desktop, and the user can do whatever they want. They can click whatever they want. And so you have this idea of events and the need to communicate that an event has happened to a component and between different components. And so Smalltalk introduced this idea of messaging. And Alan Kay, who was one of the lead designers of Smalltalk, said we're passing messages between objects. It's object-oriented programming, if you will. And he coined the phrase object-oriented programming. And he has said that if he'd had it to do over again, he would call it message-oriented programming, because everyone since has picked up on the objects and not so much on the messages, with the singular exception of Ruby. If you ever want to know what happened to Smalltalk, it's Ruby now, except without some of the good bits. This is FizzBuzz, and actually you can kind of see the Rubiness in this code, which I like. But yes, this is FizzBuzz in Smalltalk, and you can see that the way we implement FizzBuzz is we monkey patch the integer type to have a FizzBuzz method, which I love. Why wouldn't every integer in your program need to be FizzBuzzable? And it takes an input and it produces an output and it does all this sort of stuff. But yes, but Smalltalk, this is from the Wikipedia entry for Smalltalk. Since all values are objects, classes are also objects. Each class is an instance of the meta-class of that class. Meta-classes are in turn also objects and are all instances of a class called meta-class, which I'm betting is an object. Code blocks, Smalltalk's way of expressing anonymous functions, are also objects. And so I think we can safely say that from Smalltalk, JavaScript got the idea that everything is an object. If I can just get, there we go. That was the last one. But it did have some other stuff in there as well. Smalltalk was the first language where you could do reflection, because once you've got objects that are passing messages around, then it's a good idea to be able to say, what kind of object are you and what messages do you accept? And so it introduced reflection. It was the first language that had a dedicated way to write out debug information, because where would you put it on a graphical user operating system? So there was actually a console window, and any application that logged a console, it would go to the console window. It was the first language that had a virtual machine, so Smalltalk compiled to bytecode, and then it would run on a virtual machine, and you could re-implement the virtual machine for different platforms, and you wouldn't have to recompile the code. And I've put JIT. So Smalltalk did have a JIT. It took that bytecode and the virtual machine, compiled it to machine code on the fly, and then ran it on the local machine. Except Smalltalk wasn't actually the first thing that shipped with a JIT. Bonus point, can anyone tell me what the first thing that had a JIT compiler in it was?
What is a JIT compiler?
A just-in-time compiler. So it takes either text or bytecode, like Java bytecode or .NET IL, and on the fly, it compiles it into machine code for the machine it is running on, and then that becomes part of the program. And it doesn't compile anything until it's just about to use it. So yes.
Lisp had it.
Nope, Lisp sort of had a JIT, but it didn't. No, the first thing that had a JIT compiler was regex, regular expressions. And the first regular expressions implementation actually came out in 1968. And the thing that was running the regular expressions, it was actually easier to turn the regular expression into machine code and then just run the machine code than it was to write an interpreter to run the regular expression, and orders of magnitude faster. And just for shits and giggles, yes, this is FizzBuzz in regex. If you run that on a string that contains space-delimited numbers, it will replace anything divisible by 3 with fizz, anything divisible by 5 with buzz, and yeah, I have no idea how it works, but if you're interested, it's on GitHub, there's a gist. It's by a lunatic called QuackBarC, apparently, and at the bottom of the README for it, it says this. And it's just, yes, it's either that or why some men just want to watch the world burn. Okay, Lisp, functional programming, people have kind of carried on doing it, and there were a few things along the way, but the first major thing that upset the Lisp train was ML. ML was a functional programming language, and ML became Camel, which became OCaml, which is Camel with objects, which became F#. And so essentially, most things haven't changed here. And here you can see we've got like pattern matching. So we've got a case statement there, and then various branches off that, and we can declare functions and we can throw them around and all this sort of thing. But the thing that we're interested in, because I've decided to focus purely on JavaScript, is equals greater than. So ML introduced the idea of the fat arrow function. That hadn't been seen before. If you look at sort of earlier things, they used the pipe, variable name pipe, and then just go straight into the function body. But this used fat arrows for lambda syntax. Also, in the 1970s, we got Scheme. And Lisp, Lisp had evolved and people were building Lisps and using Lisp and building complicated things in Lisp, and true artificial intelligence was only 5 years away. Abel and Sussman, and at least one of them was called Gerald. I can't remember which way round it goes though. They were teachers at MIT. They taught the Computer Science Introductory 601 course. And they wanted to teach computer programming from first principles. And so the way they decided to do this was to create a simplified version of Lisp called Scheme. And Scheme, it's insanely simple to implement Scheme. You can do it in a few hundred lines of code. I think people do it in less than that, but it is a ridiculously easy language to implement because once you've got the list processing done, you've written your parser and your lexer and your tokenizer and everything. And so they created Scheme, and by the end of this introductory course, you knew how to write another scheme in Scheme. It's a whole Ouroboros thing going on there. It looks essentially a lot like Lisp. It's got different keywords, but we have, so we've got modulo now, x and 15 and 0, and we've got equals as an operator, and so on. But Scheme is essentially just Lisp. And there's nothing syntactically that JavaScript has taken from Scheme or from Lisp. But when it's 1995 and you're sitting in your office working on new sort of Chrome for the refresh button or whatever it is Brendan Eich was doing that day, and Mark Andreessen sticks his head round the door and goes, "Need a scripting language that runs in the browser by the end of next week," and you know a lot about designing and implementing programming languages, you go, crap, Scheme. And you write Scheme and you make it run in the browser. And then you present this 10 days later to Andreessen and all the other higher-ups at Netscape, and they say, "What the hell is that?" And he goes, "It's Scheme, it's like Lisp, but easier." And they said, "No, we're competing with Java applets," which is what people were using for interactivity in web pages. You wanted a mouse over to change the color of a button, you had to install the JVM. And they went, "We're competing with, make it look like Java." And so he took a Scheme and then he just made it look like Java. But under the covers, it was still a Scheme. And the first version of JavaScript, all the things that you can do in Scheme with Lisp, you could do in JavaScript with arrays. So things like push and pop and head and rest and that sort of thing. So yes, where are we? Okay, so then, tried various versions of this, and I kind of went Smalltalk to C++ as well as C to C++. But actually, there's not a lot from Smalltalk that made its way into C++. It was really just the idea of object orientation. And so it actually kind of inherits from Simula rather than Smalltalk. And obviously, it inherits from C as well. So C++ was created in the mid-80s by Bjarne Stroustrup. I worked with him for a while. He actually works for Morgan Stanley. And every now and then he would send emails to everyone at Morgan Stanley. That's a lot of people. He couldn't remember the name of the group that he actually wanted to send something to. And, well, I'll send it to everyone, and then the people who need it will get it. I was like, hey, you've got a Bjarne email, hurrah! This is Bjarne. And this is what he said about his programming language that he'd made. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg off. This is FizzBuzz in C++. So, like I say, my first job, I learned C. And then whenever it was Windows came along, Windows for Workgroups, specifically 3.11, it's kind of like, oh, we need to start building Windows applications. And they told, because we were talking about this earlier on, and they said, go and find the best programming language for building Windows applications. And earlier on, I mentioned VB3, Power Builder, and Gupta SQL Windows. I forgot, I did look at C++ as well, and specifically MFC. And so you get the C++ equivalent of the C programming language book, and it's got Hello World, and you're kind of like, well, that'll just be printf. Oh, no, it's cout, less than, and then whatever you wanted to print. Which, just why? Why? I don't get that at all. It's so weird. And so I kind of went, no, not doing that, and I ran away, and then spent the next 5 years of my life doing Gupta SQL Windows. So I may not be the best person to judge these things. But C++, the thing that it added that C didn't have was first-class support for errors. Things are going to go wrong when you run your application. It's going to try and open a file that isn't there, or it's going to try and write to a file that somebody else has got open and they're reading it. It's going to do things, and there's no way that you can check in advance and say, is it going to do this? And then sort of try and do defensive programming, because computers can do lots of things at the same time. And so you could say, is it okay to do this? And then the computer comes back and goes, yes, you can. And then something changes that says you can't do this anymore. So errors are going to happen. C dealt with this by returning sentinel values from functions, and then there was a getLastError function that you could call, which would give you details about whatever had gone wrong. But C++ introduced the idea of exceptions, try, catch, and throw, and using exceptions as a way of handling errors in your application. And the battle is still raging to this day as to whether that's a good thing or not. I love exceptions, they're really helpful, but there's a whole bunch of people who won't use them at all and want result types and option types and maybe types and set category theory things going on.
And those people should go and write Go.
They
That's
should.
why it's called Go.
They absolutely
you can
should. Just
go and
go.
write it.
Go,
Yes.
write, go. And have fun with your square bracket generics.
Sorry, just for the record, I should
Yes.
say that try, catch, and exceptions were actually first invented with ML rather than C.
Were they really?
Yeah.
There you go.
Turing award for it.
I will update the talk for the next time I do it. Thank you very much. Okay. I love it when that happens. Yeah. I get this. It also happens because when they go up on YouTube and you just get, this person doesn't know anything.
I have talks now which are like Jason's ship. Every part of the talk has been replaced with a correction from the
ship of
audience until the
Theseus.
original talk isn't there anymore.
Yes. No, one of my slide decks actually has a list of the YouTube commenters who corrected my mistakes. I think that was Programming's Greatest Mistakes. But yes. The thing is, you can talk like this for an hour and just lay down knowledge for it. You say one thing that somebody knows is wrong, and on YouTube they will call you an idiot and a dope, and you know nothing. So, among the list of things I didn't know when I started working on this talk is that there is a programming language called Self. Who knew there was a programming language called Self? Yeah, it's usually like one or two people, and you've seen this talk before, so that doesn't count. But no, do not. It's saying shut down. Stop the telly.
Who knows how to use a television set?
Make the telly stop doing the thing. Help! Help!
Press the button.
Any button?
Well, it's a touch screen, so.
Oh, okay. I think I just turned it off. She said press a button.
But the button on the.
I should have pressed it on the screen.
Was that a dialogue saying we're going to shut down?
And we said it, okay. Shut it down.
Oh, okay.
Wait.
Sorry, we have to reboot the television.
Programming's greatest mistakes.
Yes.
Smart televisions.
Sort of, yeah. So Self took some ideas from Smalltalk, but it was a dynamically typed language, and so we've got APL in there as well. Yeah, Self, it was like the first programming language where they went, let's try and make programming like fun and pleasant and a nice thing to do rather than a drudge. And so they had lots of interesting ideas for this. And so Self is an object-oriented programming language, but it doesn't use classes. It uses prototypes. Self is the language. I thought prototypes came from Scheme, and it turns out if you do object-oriented programming in Scheme, you are essentially using prototypes, but they hadn't thought of that in 1975, and so Self actually came up with the idea of prototype-based object-oriented programming, and then somebody else came along and went, oh, you could do that in Scheme. Let's add a new chapter to SICP. So yes, this is not FizzBuzz in Self, because I couldn't find enough information about it to learn it well enough to write FizzBuzz in it, and I couldn't find FizzBuzz in it, and so we have animal is an empty object, and then dog takes animal as its parent, and then anytime you want to create an instance of dog, you basically copy the prototype, at which point you can do anything you like to it and just make horrible things happen, and thank self for that. So yes, prototype-based object-oriented programming, which JavaScript uses because it's a scheme, came from self. 10 years after C++ came out, Sun Microsystems went, we suck at C++. We should build something that makes up for us sucking at C++, which, you know, goes right back to Fortran. And so they created James Gosling, while he was working at Sun Microsystems, created a programming language called Oak. And I took the piss out of Kenneth Iverson earlier on for calling his programming language a programming language. Java was originally called Oak because James Gosling could see a tree out of his window. And I just wanted to be in that conversation. Why is it called Oak, James? There's an oak tree outside my window. Right. I'm going to marketing. So it became Java. This is FizzBuzz in Java. Because you can tell we've got a sound factory to produce the things that we're going to print. And I mean, if it was really, it would sort of have dependency injection and a whole Spring Boot thing, and probably a sound factory manager strategy or something. And so finally, after all these things, Fortran going through all these different permutations and Lisp and everything else, we get to JavaScript. 1995, JavaScript comes out and combines all these lovely features into one abomination. It is very much like my worst programming language ever talk. You've just gone, hey, we'll have that from there, we'll have that from there, and oh, that looks nice, let's have that as well. And that's JavaScript. Except, and fortunately, it didn't stop evolving in 1995, although JavaScript has challenges evolving. You cannot introduce a breaking change into JavaScript. If somebody uploaded a page to the web in 1995 and they used JavaScript, because it only worked in Netscape Navigator, and let's not even talk about VB script. But yes, they used JavaScript, and that page is still up on their web server. Then if you go there with the current version of Chrome, that JavaScript will still work. And that is an astonishing achievement. And yet, despite that, they have actually managed to evolve it along the way. And these days, it looks like a modern syntactic sugar all over the place programming language. Under the covers, it's still a hideous nightmare of Boschkian proportions, but it looks nice. But it has continued to evolve. And one of the things that it's evolved from is this language, C#, which came along in 1999 and inherits directly from C++. It does. I did this talk with Mads Torgersen in the audience in Denmark last year. C#, Microsoft were inspired by making a simpler version of C++, which couldn't have memory leaks because it had a heap and a garbage collector, and would compile to intermediate bytecode so that it could run on any version of Windows. But yes, no, it definitely wasn't, because Sun wouldn't let them make a Microsoft version of Java. But yes, so C#, I think I'm right in saying that .NET actually introduced the idea of task and task-based concurrent programming. And other languages have implemented it, and they call it future, or it's called promise in JavaScript. But they're basically the same thing. It's a variable that represents the fact that something is happening, and you can check on it and go, have you finished? But that's not efficient. What you want is a way to say, when you've finished, call me back and we can carry on doing something here. And if you ever wrote task-based code for like WPF or Windows Forms to do database things without making the UI freeze, not responding, would you like to wait? But yes, you would say task.do this, .continue with, and then have to try and make sure that it all still had the right context and everything. And so in C#5, yes, we got async and await, which has been enthusiastically adopted by JavaScript, Rust. It's quite difficult to create a new programming language these days without somebody turning up and going, when are you going to do async await?
The really interesting thing, just because this is a .NET group and we talk about JavaScript a lot, is I think async await is a wonderful example of how innovation happens in .NET, because first it was the parallel tasks library, which wasn't a change to the language or the compiler or anything. It was a thing you could install that made stuff happen. And so many people liked it that they went, this probably gets its own keyword in the next release, and it did. And that's where async and await came from.
Yes.
Which I think that's like a really nice way. We can put this out there as something we're not committed to. Because once it's in C#, you're never taking it away.
Yeah.
It's like JavaScript. You can't remove anything from the language.
No breaking
people shout
changes.
at you and throw things. So anyway, yeah, I just thought that was a nice little digression.
So JavaScript continues to steal stuff from other languages, and other languages continue to steal from each other. And you build a new language these days, and you have to acknowledge a debt that goes all the way back over all kinds of prior art and ultimately ends up at Fortran, which was just the whole idea of a programming language. And so I think that's interesting, and I talk about it, and hopefully you did, and you listened, because that's it. And don't go home. The go home is there because this was the closing keynote at NDC London, but we've got a whole other thing to do. But go and grab some sandwiches and drinks and stuff.
So what we're going to do, we're going to take a short break. We're going to move some furniture, grab a drink, grab a snack, and then we are going to put, so the way the park bench works, we're going to put 4 chairs at the front, and I'm going to put people on 3 of them. And if you have questions, Mark will be one of those people, so any questions from his talk can kind of kick this off.
Yep.
If you have questions or anything you're curious about with .NET, you can ask them. If you have a question that's more of a statement, you get up and take the empty chair. And somebody else will then stand up and they will go and sit down, and the whole thing kind of flows. And
if somebody else asks a question, and you go, the world needs to hear
one.
my answer to this, then
you are welcome to get up. I am going to video record this, but anybody who is captured on video, I will share a link with the folks who are here tonight just so you can take a look at it before it goes public on YouTube, just in case anyone says anything that they wake up in the morning going, I shouldn't have said that about my boss live on the internet. So yeah, take a couple of minutes, grab a drink, grab a snack. We're just going to move some furniture around, and then we're going to do that.